So hi everyone. Today we are going to present some recent work on contact-implicit model predictive control. I am Simon and this is Taylor, and we are two PhDs at Stanford, and we are graduating pretty soon, looking for a postdoc position as well as a research scientist position in industry. So being able to do control through contact is one of the grand challenges of robotics, and I've put those videos from Boston Dynamics because I find them very inspiring, but at the same time they are nice enough to share some of the failures, reminding us that this problem is actually a very tricky problem to solve. So with this work, we wanted to focus on dynamical systems that make and break contact with their environment. And we wanted to be able to construct tracking control policies that are able to react to unexpected contact events, and that can also leverage contact surfaces to improve the tracking performance. So one of the method of choice for tracking control in robotics is linear MPC. And the idea is pretty simple. You linearize the dynamics about the reference trajectory that you want to track, and you also linearize the constraints as well as taking a quadratic approximation of the objective function. And if you put all this together, you get a quadratic program or a QP that you can solve very efficiently online.
So for systems with non-smooth dynamics, we'd really like to use a bunch of these great tools from linear MPC. But there are a couple of challenges with this. So if we have some reference trajectory that we want to track, if we perform a linearization about that, there's some region around the reference trajectory where this linearization is useful and valid. But when we have non-smooth dynamics, for example, we have an object contacting a surface, the position is going to be non-smooth, and as a result, the velocities are going to be discontinuous. So the potential region around the reference trajectory where linearizations are valid is probably a lot smaller if there's any. And it's unclear if this is a really good approach for control.
So to avoid this issue, we are going to linearize dynamics, but only partially. So just as a reminder, I'm going to describe what the contact dynamics, how the contact dynamics is expressed in our formulation. So we express it as a feasibility problem. We want to find xt+1, which is the state at the next time step, subject to some constraints. And the first constraint is the free-floating dynamics of the robot, which means, which is the manipulator equation. We also have some constraint on the interpenetration constraint between the robot and its environment. We don't want the robot to go through the floor, so we have some sign distance function constraints added to this problem. And finally, the last constraint that we have is a complementarity constraint, which encodes the binary switching behavior of contact. So if you are in contact, you can experience forces, and if you're not in contact, you cannot experience any force. So if you put all this together, you get a nonlinear complementarity problem, or NCP. And what we are doing in this work is that we are going to linearize this NCP problem about the reference trajectory, but only partially. So we are going to start by linearizing the free-floating dynamics of the robot, also linearizing the sign distance function, but we keep the complementarity constraint untouched, and we end up with this formulation. It's a linear complementarity problem, or LCP, which is classical formulation of contact dynamics, but here it's linearized about a reference trajectory.
There are a number of benefits to using an LCP formulation online in a policy. The first is that you'll notice that we strategically linearize the dynamics. So we're keeping all the complementarity constraints. And what this allows us to do in the policy is preserve contact reasoning, and we can actually change the contact mode sequence or adapt the timings of the contact sequence online. And we can demonstrate this with a really simple system that we call pushbot. It's basically a pendulum that we want to maintain in an upright nominal configuration. And the policy doesn't have any sort of contact mode sequence defined for it. And here, when we apply disturbances to the system, the policy is able to generate new contact mode sequences online, where it pushes against the wall in order to stabilize and push itself back to the nominal configuration. And that's a really simple example, but these policies can also be used for much more complicated dynamics. So this is a centroidal dynamics model for a quadruped. We have 4 feet, and we have the body of the robot, and we're going to apply a really large disturbance to the system. And it's able to generate a new contact sequence, adapt to mode timings in order to recover, and then eventually walk back to the origin. And this is all possible because we, in the LCP, still have contact reasoning. Additionally, there are a lot of computational gains that we get by solving the LCP instead of an NCP. And basically, this enables us to have real-time performance to run the policies online. So under the hood of the LCP is a linear system, basically an AX equals B set of equations that we need to solve. When we perform the linearization about the reference trajectory, this is shown here is basically the A matrix in that system. When we perform that linearization, we can actually pre-compute all of these values shown in red. Further, we can pre-factorize all of this part of the matrix. So then online, all we need to do is fill in the white values and factorize those. So this substantially reduces the computational cost of linear system solve and really enables the real-time performance of these policies.
Yeah, so coming back to the linear MPC, the only thing that we have to change to incorporate contact reasoning is to remove the linear dynamics constraint and replace that with LCP dynamics. And in order to solve this trajectory tracking problem, we will have to evaluate the dynamics, and this requires to solve the LCP problems. And for this, we have devised a custom primal dual interpoint solver. We also need to evaluate dynamics gradients, and for this, we differentiate through the LCP problem. And to do this, we are using the implicit function theorem, which can give us the sensitivities of the solution outputted by the solver with respect to the problem data. So in concrete terms, this would mean computing the gradients of the next state, xt plus 1, with respect to the current state of the system xt, or computing the gradient of xt plus 1 with respect to the control inputs ut. And yeah, so for this implicit function theorem, the nice thing about this is that the matrix in the middle has been computed during the solve of the LCP. It has also been factorized during this solve. So the only thing that we need to do at this stage to get the gradient is a back substitution, which is going to be extremely cheap computationally.
So the CI-MPC policy is available as an open source implementation. You can visit our GitHub website, DojoSim, and look for this package. You can also download it from the Julia package manager. And all the examples we're going to show are also available in notebooks. So take a look at the GitHub, give us a star, and hopefully it's useful for projects you might have. So we'll show off a couple of the results. We're able to use these policies to control Raybird hoppers, quadrupeds, bipeds. So it's a really general policy that can be used for many types of robotic systems. So in this first example, we have a planar quadruped, and we design a gate for it offline. So that's some sort of reference trajectory. And then we're able to tune our policy. So basically, we just manually change the weights in our cost function in order to get good tracking behavior for the nominal model on flat ground. What you're seeing here is we now took that policy that we tuned, and we've added a heavy load to the back of the quadruped, and then use that same policy. And you can see that the policy is able to recover from this substantial amount of model mismatch or large disturbance, and is able to keep walking and track this reference gate. One other thing to say about this is if we then retune the policy, knowing that we have a large load on the robot, we can get basically perfect tracking performance with very little effort. And I think a really interesting research direction actually is to just auto-tune these policy cost weights and do some sort of adaptive learning online so that you can handle situations like this with no designer feedback. In this example, we have a biped with feet. So it's a flamingo robot that was designed in the late 90s. And similarly, we generate a gate offline for the flamingo on flat terrain. We tune the policy for this terrain. And then we can use that same policy to walk over unmodeled terrain. So in the middle, we have sinusoidal terrain that's unmodeled in the policy. And at the very bottom, we have this incline. An incline here is 10 degrees. And this is basically double the incline that the original authors were able to get the actual hardware to walk up in real life. And then in this last simulation example, we really wanted to test, how good are these policies to rejecting disturbances? So we performed a Monte Carlo simulation where we sample initial configurations that are offset from the reference's initial condition, and then we see if the policy is basically able to recover from these configurations and return the system to the reference. And on the left, this is the planar quadruped again. You can see that eventually the policy is able to drive all the systems back to the desired gate. And then on the right, this is a Raybert hopper, and similarly, policy quickly drives all the systems back.
All right. So we've done a lot of experiments in simulation, and recently we've been trying to get things running on hardware. So we did some experiments on the Unitree A1, which is a quadruped robot, and we were able to run contact-implicit MPC at rates ranging between 200 and 500 hertz. So to get a behavior onto the hardware, the pipelines works like this. So we have first an offline step where we are doing contact-implicit trajectory optimization. Then the next step is to verify that we can track it in simulation using contact-implicit MPC. And finally, when we are satisfied with the results, with the tracking results, we can just port it on hardware and get the nice behavior on the quadruped, the real hardware. So we've done this for this stepping policy. We can also do it for a trotting gait. So we have followed the same pipeline, and at the end we can get the quadruped to trot. There are like many potential applications for using those templates that are computed offline and chaining them together to get really complex behavior online, doing some really complex tracking. Additionally, we've been testing the robustness of the solver, of the tracking controller, and testing that it can reject some external disturbances and can adapt its mode sequence and contact timings when it needs to do in order to better recover. So for this project, I've been extremely lucky to work with Taylor and also Xian Li and Chuo Yang at CMU, as well as Max Schwager and Zachary Manchester, our two advisors. So with this, I'll thank you for your attention, and I will be really happy to take any question now or offline at the poster.
We have time for one quick question.
Hi, Alessandro Sacon. Very interesting work. One question I have is, I saw that you have this situation where you have multiple contacts, simultaneous contact with the feet of the robot. And here you're talking about linearization. And essentially, there's no possible to find a linearization in that case, because the only approximation you can get of first order is actually only positive homogeneous. Can you comment on this?
So yeah, I mean, we have done some linearization of the sign distance functions, but we didn't linearize. So I hope I understood the question well, but we have done linearization of the sign distance functions and things like this, but we didn't linearize the complementary constraint, which allows us to still keep reasoning about different contact modes, and so we don't linearize the contact modes at all. We can still reason about being in contact or not being in contact, being in sliding mode or sticking mode, we can do all this online.